Hey guys, how's everything going? Today, let's take a look at number 98, a valid binary search tree. We are given a binary tree. Determine if it is valid binary search tree or not. A binary search tree means the left subtree of a node contains only nodes with the keys less than the node's key. Okay, so the numbers to the left are smaller than the root node. Number to the right are bigger than it, and every subtree will be the same. Well, the first solution comes to my mind is just recursion, right? If we can determine one node, then we can handle all the nodes. We just follow by the definition. We just need to find the if divide three conditions, right? First, if the left node is valid. Second, if right is valid, and then last, all the nodes to the left are smaller and all the nodes to the right are bigger. That could be deducted to the biggest of left node is smaller than 2, and the minimum of right tree would be bigger than 2, right? Yeah, let's define the recursion function. I will always call it a walk to get a node and return as we said before. It should be return first is left valid and is right valid, and max of left is smaller than node val, and the max of right, no, minimum of right is bigger than node val, right? Yeah, obviously these two could be just get from walk, but the maximum and minimum must be also be retrieved from this walk method. So the walk recursion function does not need not only the walk method needs to return the status, but also need to return the min max of the subtree. Well, that makes us clear that we need to return first the status, and then we need to return the min of current, max of current. So is left valid, min of left, max of left could be retrieved from the recursion. And then we can do the same to right, right? Min of right, max of right, and walk to the right. What's the edge case? The ending condition would be if the node is null, right? So if null must be true, and the minimum used to compare to the comparing of right node. So it must be bigger than the current node. So it must be a number bigger than anything. So it's infinity. Maximum is negative infinity. And minimum current. Minimum current actually is the current node and the minimum of left node and minimum of right node, the minimum of all three. But if the tree is not valid, then the status will be reflect that. So we can just update the left tree, right? Because left might return infinity. That's what we need to update. So it's math minimum min of left min of left node val. Max is the same. Max of right node val. And then finally we return walk root, and the first element would be the result. Let's try run the code. Yeah, accepted. Actually, I have done these questions just before this video is recorded. I've recorded all the videos, but I happened to click the delete button, so I have to record it then. So sorry if the video seems like if I feel like if I sounds a little depressed. Yes, that's the real emotion of me currently. Time would be every node would be traversed for only one, so it's linear. N is the number of nodes. Space, we use this array to return result, but it's actually it won't be stacked. The core stack will be stacked, but the return value will not be stacked. It will after it is used, it will be recycled. So the space I think would be linear. Worst, right? Because there's a core stack. Okay, so this is the first solution to our problem. The return of three values seems a little weird, I have to say. We can actually improve this. The idea is that rather than we collecting the min max from bottom up, we might just need to pass the values top down, right? Let's say when we determine if 2 is valid, actually we're collecting the minimum from 1 and maximum from minimum of 3, maximum from 1. But on the contrary, for 2, I think it's valid because yes, there's nothing on top of it. But for 1, it must be smaller than 2. 3, it must be bigger than 2. So the problem becomes not collecting the min max from the bottom, but pass down the restriction. That reminds us we can change this recursion method a little bit and pass it down with min max. With this, we could just if it's null, we could just return true. And if it's left valid, it's just like walk this. What's the mean? Well, it might be smaller because the mean is for 2, the mean is passed, right? And for 1, okay, we need to check the minimum. Yeah, minimum. For 1, it must be smaller than 2, and the number mean passed by it, right? So it should be math minimum node val mean. Oh, I made a mistake. The min max is not the bottom up min max. It means what's the mean range for current node. So it's actually this should not be mean but be max. We could do the same to the right. Is right valid? Walk. Yeah, and then finally, if it's if left is valid, if right is valid, yeah, sure. And then finally we return is left valid and is right valid, and what? And the node val is smaller than max. Node val is bigger than min, and we could walk to root with a min of minus negative infinity and the positive max is infinity. Let's try. Yeah, we're accepted, and oh, we're not accepted. It's wrong. Let's check it again. Wow, the minimum should be, so node should be bigger than the minimum. It's true. The max would be infinity. Yeah, sure. Node is null. Left walk. Left. Left must be smaller than the max, or node val. Yeah, it's right valid. Right, so it should be bigger than the node val or the minimum. Yeah, left is valid, right valid, and node val is smaller than max, and the node val is bigger than minimum. And we return walk root infinity infinity. Yeah, but why would we return false? Okay, for two, obviously we got to 1, right? So left valid 1, minimum should be 2. Oh, my bad. I mean, it should be smaller than max, bigger than min, smaller. Yeah. So left valid. So we check 1 if it's smaller than 2. Yeah, and because it's null, we return true. So left valid, right valid, and for 1, it must be 1 smaller than 2. We forgot to pass down the minimum. My bad. Minimum is okay, but here max is okay. So wow, this is a huge mistake. Yeah, we accepted, and this actually just another form of recursion. The time, every node is traversed only once. Space, actually the same. The max worst case is same as above, right? So I say same as above. Now the interviewer might say, okay, you are using recursion for tree traversal. Could you rewrite it into an iteration fashion? I say, yes, we could. So how will we do it? It's like the same as this one, right? You see, we are checking each node if it is okay with the min max. If it's okay, we just pop it and just ignore it. And there's nothing we need to do. That reminds us that we just use a stack to push each node, of course with the min max. So the stack would be root the minimum is just as the same. I push this in, and let top. While there is top, what we check, we check these conditions first. If it is not matched, we return immediately, right? So if top val is bigger or bigger, okay, my bad. And then we destruct it, node min max top. If the value is bigger than max or smaller than min, return false. And yeah, the default is true. Now after check, we need to push the child nodes in it, right? So the order doesn't matter here. And we say if there's an F node, we will push it in. The minimum just is here. Min doesn't change. Max would be node val max. We do this the same to the right. And yeah, I think we're done here. The iteration here actually has the same time. It would be this is the same, so linear time, but space. There's no call stack. That's much better. So, but we use a stack here to keep track of the child node. Every time we push one, and then we will pop one, and at most push 2n. So the worst case is that half of the node are stacked in a stack. So space for worst is be O n divided by 2, so it's linear. Let's try to run the code. Cool. We're accepted. We're not accepted. Cannot read property val of null. Null, so this will be possibly by null. Null. Oh yeah, my bad. So for null, it doesn't matter. We just continue to skip. Yeah, we're accepted. And this is our third approach of this problem. And actually, there's another problem. The other solution, which I didn't think think of. It's actually in a solution. If you're interested, please take a look. It's very interesting. So, oh, my bad. So the idea is very interesting. So for every binary search tree, there's a unique characteristic. Is that if we do the in-order traversal, it will generate an ascending array. You see, because for the simplest form, a left will be smaller than middle and smaller than the right. So if do the in-order traversal, it will generate 1. This is if 3 is here. This is invalid. So 1, 5, 3, 4, 6. We met a number 5. 5 is bigger than the next one, 3. So it's not valid. If it's valid, 1, 3, 4, 5, 6, it's a valid BSC. So that reminds us actually. I didn't know this until I saw the solution list. So use in-order traversal. This is a very interesting angle to look at the binary tree problems. Maybe it will help us solving other problems also. In-order traversal. It must need to ascending array. Yeah, let's try to do that. How could we do the in-order traversal? Well, in-order traversal means the middle is we handle the left node first, and then the middle, and then the right node, right? So for this case, we made 5 because there's left node. So then we need to push 1 in and handle 1 first. If 1 has another left node, we need to push that in, right? And then after we pushed all them in, and we could start popping, and we handle this. Okay, there's no child node. It's done. 5, and it's done. And there is a node, the right node. Then we push it in, and we push it as we always do. So here we use a stack to store the batch of nodes we need to process, and then the nodes we need to process, and then we create a function called push. We will push a node into the stack. How we push it? Well, we will push it until all the left nodes are stacked. Push node, and the node left, right? Yeah. After we push it, this is a push, and we can start collect, right? I create a collect method. So when we collect, we just pop one node. while there is still nodes to pop, when we pop the node, it must be there is no left node, right? Because we already pushed them. So we collect the result. So if top val is smaller or equal than pre value, we need to cache prev. Let prev equals infinity. No, minus infinity. If it's smaller than it, then we return false, right? And then it's okay. Then we pop it, and then we check if there's right node. Top right, we push top right. Yeah, I think this is done. So I think separating the function will make the code clearer. Someone just put this while node in this while loop. I think, yeah, modularization is important. So, and now we push the first node in, which is root, and then we start collect. Of course, here we need to return true as default. Let's try to run the code. Oh, the dot is missed. Submit. Wow, false. Why? Let's analyze our code. Stack is okay. When we push, we will push until all the left nodes are there. And prev. Oh, we forgot to update the prev node, right? Prev equals top. Wow. Yeah, we accepted. And let's analyze the time and space complexity. For time, each node actually is traversed only once, so it's linear. A space, we use a stack, but we don't stack all the left child and the right child. We only maximum stack the left node. So for the worst case, it's still linear time if all these nodes are a straight line. Yeah, so I think that's all for this problem. It's very interesting that we could use four approaches to this one. The in-order traversal and the iteration rewriting of recursion is very important. If we want to, I think we need to practice more in the future. Maybe I'll do some videos about all those pre-order, in-order, post-order, and the iteration and the recursion thing. Yeah, at least there will be 6 programs of how to do the traversal, and also the BST, and oh yeah, BS first, search BFS and DFS, in-order traversal, post-order. Yes, 5, and so the other one 10 milligrams. Yeah, and I will do it soon. So stay tuned. Hope you enjoyed this video. Hope it helps you. And yeah, see you next time. Bye bye.